Let's take this opportunity to review the attraction and growing interest in the realm of permanent magnet recycling. Currently, waste magnets are generated from both production scraps and end-of-life sources. The evolution of electronic automation in the area of sensors and switches, and magnets used in motors and generators is creating an increased demand for the raw materials required to produce magnets. Proliferation of the use of magnets in electronics devices, automotive and transportation components, medical devices, manufacturing and industrial automation and household appliances, all contribute to a growing need for strategic and critical magnet materials. The renewable energy industry that utilizes permanent magnet generators are an area of strong demand. Some designs, such as particular types of wind turbines, contain large quantities of permanent magnets. Traditionally, the infrastructure to recover or recycle magnet scrap has been quite limited. In today's market conditions, there has been an increased recognition that additional efforts are required to develop a resource recovery strategy to assist in ensuring the secure supply of the critical materials required by the magnet industry. Let's spotlight some of the key areas that need to mature, focus on the collection, pretreatment processing, refining and the development of a formal market infrastructure for scrap permanent magnets and the related secondary commodities. First of all, let's identify the various elements contained in different types of magnets. Permanent magnets are primarily manufactured into 4 distinct classes of magnetic alloys. The performance, temperature tolerance, and power of each magnet depend heavily on its specific combination of rare earth, transition, and base metals. One popular type of magnet is the neodymium magnet, with a typical composition of approximately 30% neodymium, and from 64 to 69% iron, and 1 to 2% boron, along with trace elements that range from 0 up to 3%, that may contain a mix of aluminum, cobalt, niobium, dysprosium, praseodymium, gallium, or terbium. Neodymium magnets are almost always plated or coated, because they are highly susceptible to oxidation and corrosion. Coatings also make these magnets less brittle, reducing the risk of chipping or cracking during use. The industry standard most commonly uses a triple-layer plating of nickel-copper-nickel. A durable matte gray zinc coating is also often used for heavy-duty or industrial applications. Another type of magnet is the samarium cobalt and is referred to as an SMCO class of magnets. They are produced in 2 distinct commercial alloy series. The 1-5 alloy contains approximately 36% samarium and 64% cobalt. And the second in the series is the 217 alloy, with a cobalt content of 48 to 52%, and samarium with 23 to 28%, and iron ranging from 14 to 18% along with 5 to 8% copper, and 1 to 4% zirconium. Alnico magnets have a composition of aluminum, nickel, and cobalt, and often are found including iron, copper, and titanium. Common ferrite magnets, also known as ceramic magnets, are primarily composed of iron oxide, Fe2O3, the same compound as rust, and are combined with either strontium carbonate or barium carbonate. Now that we know some of the different types of magnets, we may move on with the first challenge that we wish to spotlight, and that is in the collection of magnets from various waste streams. The sorting of waste devices that contain a magnet from other waste materials is typically achieved by a manual triage step. The second challenge we wish to identify is the treatment of the magnet-containing waste streams, by the source separation method of processing the scrap materials by dismantling the devices to reduce the total amount of non-magnet materials or to entirely liberate the permanent magnets. The potential exists, for some selected liberated permanent magnets, to be reused or sold as usable magnets, otherwise the remaining magnets or magnet materials may proceed along the scrap recovery pathway. Scrap permanent magnets, like neodymium, must be stored and transported in sturdy, steel-shielded containers to contain their magnetic fields and prevent dangerous unintentional attachment. Separate individual packaging of magnets using non-magnetic spacers like cardboard or foam may be used within the container. The storage or transport containers must be adequately labeled with hazard warnings. It is common practice, with source-separated magnets, to package individual or small bunches of magnets into a sandwich, wrapped securely with layers of cardboard or foam materials, in order to avoid a sticky, unmanageable mess. The magnet sandwiches may then be packed into a steel storage or shipping container. In a further processing step, the magnet sandwiches may easily be thermally treated to both demagnetize and get rid of the packaging. Mixed magnet scrap. Source-separated permanent magnet scrap may contain any mix or type of magnets, such as neodymium, samarium cobalt, alnico or ceramic ferrite magnets. And may also include any form of coated or uncoated sintered or bonded polymer molded magnets and flexible magnet materials. This mixed magnet scrap may now be prepared for the further steps of processing or refining. Typically, magnet grinding swarf or sludges are handled in their own distinct pathway that includes solid-liquid separation and briquetting. Now, the practical reality that we encounter is that it is just not economically viable to attempt to overcome the technical difficulties required to separate tiny, deeply embedded magnets from microelectronics or attempt to sort or isolate small sensors and switches from automotive or appliance scrap. The standard practice in a scrap yard or e-scrap operation is to mass shred all of the bulky scrap materials, which transforms the mix into a more uniform material handleable size, that then may be further automatively segregated. When scrap materials that contain magnets are shredded, the magnets travel along with the magnetically segregated steel fraction. The magnets tend to fragment and form clumps. Fragmented magnet clumps are shredder fragments of permanent magnet pieces, dusts and residues that may become agglomerated into magnetic clumps that are attracted to any nearby steel, and this drags the combined steel and magnet frag clumps along the recovery path, and accumulate, and are blended or incorporated within the steel fraction. One potentially viable approach to recover the magnet materials is in the form of a remaining residue, left over after an iron energy recovery step. Then in a process, with an economic driver, the scrap iron fines and iron oxides are converted into high-purity iron powders, and the magnets are transformed into a highly concentrated mix of rare earth residues as a secondary sidestream byproduct. This approach may be further enhanced since neodymium magnets may contain up to 70% iron, and ferrite ceramic magnets may be 80% iron content. In this process, the iron fraction may be valorized, and it results in the balance of the magnet materials to become highly concentrated. In the further processing and refining steps, hydrogen decrepitation of neodymium magnets is one method that utilizes the hydrogen processing of magnet scrap. This process is commonly referred to as the HPMS technique. Exposing the scrap to hydrogen gas at room temperature forces the alloys to expand and crumble into a demagnetized metal powder, cleanly peeling away any protective surface coatings. Direct separation by physical sieving or screening of the demagnetized powder, that then may be realloyed, melted, and processed directly into fresh regenerated magnetic powder. In the hydrometallurgy refining process, magnet scrap or powder is dissolved in strong acids or alkalis to leach out and chemically separate the highly pure rare earth elements from other metals. This typically forms a product consisting of mixed rare earth oxides in the form known as an REO concentrate. In the pyrometallurgy refining method, the magnet scrap is melted at high temperatures in a smelting furnace to extract the thermally demagnetized rare earths from the molten slag. The next hurdle we wish to tackle is the formal market infrastructure development for scrap permanent magnets and their related secondary commodities. The establishment of an exchange system to facilitate the trade of this unique group of specialized strategic and critical materials may prove to be an essential step. Along with a transparent spot market platform, establishing a price index mechanism may prove beneficial. This may have the potential and might be able to expand beyond magnet materials to encompass the spectrum of rare earths and critical commodities. The opportunity to establish a pricing index or market reference guide either on a worldwide basis, or for specific regions, such as the European market, North America, or other areas such as South America or Oceania and Southeast Asia regions, that are an important source of minerals, metals and rare earths. This regional market reference approach may provide a bridge that may fulfill an existing need, and fill the void to better reflect current market conditions in different geographic or economic zones. The enhancement of education and awareness of developments of infrastructure and recycling efforts across the value chain will only strengthen and mature the magnet industry. We hope to have the opportunity to engage with others interested in a resource recovery strategy, so please feel free to contact us at your convenience. Please visit us at www.waste.net.